Hello everyone, this is Kevin Mato from the Polytechnic of Milan. My colleague Riccardo Mengoni and me today will explain you about molecule unfolding with quantum annealing. This project is related to the drug discovery process, in particular in silico drug discovery. One method used in silico drug discovery is molecular docking for virtual screening. What is this? This is a method for finding the most promising molecules from a database to forward to the next experimental phases. This can be very long and complex. The approach taken to perform the virtual screening aims at finding the three-dimensional poles of a given compound when it's interacting with a protein binding site. The region of interaction in the protein is small and we can call it pocket. Given a pose in the pocket, we can estimate the strength of the chemical and physical interactions between the ligand and the pocket by computing a geometric fitting score. Every ligand from the database is evaluated separately and independently from each other. The molecular docking is divided into three more phases: the ligand expansion, the initial placement, and the shape refinement. The ligand expansion consists in taking the information related to a compound from a mol2 file and translating it into a three-dimensional model. From this model, we will identify some rotable bonds and we will maximize the internal distances. Then we will place this molecule thanks to some roto-translations inside the pocket, and then there will be some shape refinement. Our project is about the ligand expansion. Currently, the ligand expansion is taking as much time as the docking, and this phase is very much important because the quality of the ligand expansion is reflecting throughout all the molecular docking process. What is happening? We are using a tool called Smile2 3D, which is taking the mol2 file and is translating the information into a 3D model. This model, though, is not completely expanded, so we have to perform some operations on it. Right now, our main metric for the expansion is just the total sum of the internal distances. While we consider the target pocket a rigid structure, the ligand is a flexible set of atoms arranged in space and bound together by chemical bonds, where moreover the bond's length and the angles between them are fixed at some value. Furthermore, proceeding in this geometrical interpretation, we could detect a subset of bonds which can be rotated along their axes. These have the particularity of splitting the ligand into two disjoint non-empty fragments when removed. The torsionals or rotable bonds can rotate to discrete angles, and these ones will determine and distinguish one conformation from another. The rotation is performed as a matrix multiplication between the position of an atom and the matrix representing the rotation due to the rotable bond, and when we have more rotable bonds, the combination of the rotations will be just a combination of matrices. So, for our experiments, we started from a database of compounds. There are two main features here that are representing what kind of molecules we have inside our database. On the left, we have the number of atoms and the number of fragments, where the number of fragments is actually an upper bound of the number of rotable bonds, because we can say that the number of fragments divided by 2 is an upper bound for the rotables. And from this database, we took 118 molecules and we ordered them in by increasing volume. As you have may thought, the number of fragments and the number of atoms are correlated to the increasing volume of the molecules. Here we have an example of how we actually do our ligand expansion. The example involves the compound zinc 53, which is the aspirin. The first step is to find the central atom inside our molecule, and this is done thanks to a particular attribute called betweenness centrality. The betweenness centrality is a number that is computed as the total sum of the ratios of all the possible shortest paths passing through an atom over all the possible shortest paths inside the molecule. Then, after we found the central atom, we will have to detect which atoms have to be rotated by which composition of rotation matrices. And this is done thanks to something called Rotable's influence set. Basically, what we are doing, we are intersecting the set of the bonds composing a certain shortest path with the set of the rotable bonds. And the atoms that have the same influence set will be rotated by the same composition of rotation matrices. So practically what is happening, we are rotating all our torsionals, and we will end up with different sets of atoms rotated by different matrices, and of which the final position in the space will be determined by different angles. Another simplification that we did was that double and amide bonds are not rotable, and moreover we removed the hydrogens from our molecules. So now I will explain you 3 different approaches to explore all the possible conformations a molecule can take. The first 2 methods are greedy, and the second one is very naive, it's just a brute force. So with GeoDoc, which is the method that is right now employed for performing the ligand expansion, we are actually testing all the possible combinations for the first rotable, measuring the internal distance for every combination tested, and then once the best angle is found for the first rotable bond, we are going to the second one, then to the third one, and then to the fourth one. Or we could do this in a batch way, which is testing combinations for S torsionals at a time. So we are testing all the possible combinations for the first rotable bond and second rotable bond. And once we find the best combination for the first 2 rotable bonds that is maximizing the internal distance, we're actually going to the third and fourth one. It doesn't mean that you have to explore the conformations just by two, and it doesn't mean that you have to explore the conformations by 2 rotables at a time, but you could take 2, 3, 4, 10, or even more. Meanwhile, in the brute force inspection, we are just testing all the possible combinations for the 4 rotable bonds at the same time. In this slide, I would like to show you the effect of rotating our torsionals with greater degrees in comparison with just 1 degree. So in the plot on the left, you can find on the x-axis the 118 ligands ordered by increasing volume, and on the y-axis the percentage of degradation of our ligand expansion when we are rotating by 45 degrees versus 1 degree, 10 versus 1, 20 versus 1, 5 and 2 versus 1. And there is actually a very surprising result, because when we are rotating by 45 degrees at a time, the degradation is at most 4%. And on the plot on the right, we wanted to show you that actually these great results in degradation are not due to the original position of the molecule when it's taken from the mole tube, but it's actually due to our procedure of expansion.
So let's now translate the molecular expansion or unfolding problem in terms of combinatorial optimization problem. It is convenient to identify the configuration of a molecule by means of this torsion vector shown here. And again, the objective is to find the unfolded torsion configuration that maximizes the distances between fragments, which means maximizes the volume of the molecule. Okay, so in mathematical terms, this means maximizing the sum of the distances DAB, which depend on the angle theta. The distance DAB is the distance between fragment A and fragment B. Theta is enters in play in the, as you can see, as in the rotation matrix R theta, which is the multiplication of all the rotation matrices associated with the bonds with the torsions that belong to the shortest path between fragment A and fragment B. Okay, we want to translate the molecular for the problem in terms of binary optimization. The problem is inherently high order, so this means that we will get a Hugo, which means a high order unconstrained binary optimization problem. So let's start with considering a discretization of the torsion of each torsion angle theta I into the possible values, as you can see here. We can introduce then a binary variable xik, which is 1 if the torsion angle theta I assume exactly the value theta ik, and 0 otherwise. Of course, since the torsion angle can assume only one value at a time, this means that there is the constraint shown here. This discretization also induces a discretization on the sine and the cosine function of theta ik, as you can see here. These two functions are inside the rotation matrix R of theta I. This is the general form of the Hugo optimization function. The first term that you can see multiplied by A is the one associated with the R constraint that I explained before, where there is only one acceptable value for the angles theta I. And the second term is the maximization of the internal distances. Again, the internal distances is represented in this way. And it's important to understand that DAB, so the distance between rigid body or fragment A and B, could depend on m different torsions. So in this case, DAB contains them up to the mth order, which means that the highest order in the Hugo is 2 times m. Okay. What is the structure of this Hugo problem? First of all, we can say that if we want a precision in the discretization of the angles of delta theta I, the number of variables needed for each torsion angle is equal to d, expressed here. In general, given a molecule with m torsions, the total number of binary variables is then n, that is d times m. In the following, we refer to this molecule here, and we restricted our experiment for this molecule, which has 82 atoms and 40 different fragments, rigid bodies inside it, and 20 torsion angles. Okay, again, as I told you, in the case of the discretization delta of theta I equal to pi over 4, we have the following, the Hugo problem has the following properties. The linear terms increase linearly with the number of torsions, so going from 16 for the case where we have only two, where we only consider the first two torsions in degree centrality order, up to 80 variables, 80 linear terms when we consider 10 torsions. The number of high-order terms in the UBO instead increase almost exponentially. For a number of torsions equal to 2, we have just 296 high-order terms. So high-order means higher than linear, so quadratic, cubic, and so on. Up to 12 million terms in the case of 10 torsions. This means that the problem is highly complex, increasing the number of torsions, of course. Okay, one way to overcome this difficulty is to apply some approximation to the Hugos. So what we decided to do is to delete the Hugo terms that were below some certain threshold t, and this allows us to speed up the construction of the Hugos, but also to speed up the transformation from Hugos to cubos that was done using the make quadratic function available in the D-Wave libraries, and this made the problem solvable with both the D-Wave and the hybrid solver. Okay, on the plot on the right, you can see that the green column, the blue columns are the full UBOs, and then we approximated it with an increasing threshold going from 100 to 1500. As you can see, the number of high-order terms decrease, increasing the approximation, the threshold of the approximation. These two graphs show the structure, the topology of the cubos coming from different approximations of the UBOs. So, as you can see, for example, in the case of 8 and 10 torsions, the number of linear terms increase rapidly when we decrease the approximation on the UBOs. Same happens for the quadratic terms in the cubos. These now are the result that we get from the classical function, from the classical approaches, the brute force and the greedy approach that Kevin explained before. On the left it is shown the brute force approach. The blue columns show brute force without any approximation, while the red columns show the brute force solutions obtained with something similar to what we did to the UBOs, approximation with threshold 100. Okay, and these were exactly the results on the optimal volume that we were able to find. On the right, there is the same thing, but with the greedy approach. And we used the batched, where the batches have different sizes, going from 2, the blue one, 4, the red one, and 5, the green one. And maybe here you can see that the best solutions were, for example, for in the case of 8 and 10 torsions, so the largest problem were those where we split the problem into two equal sub-problems. So what about the wave results? How do they compare with these classical? So on the left, we show the optimal configuration volume found by the D-Wave and the hybrid solver, and we compare it with the best classical output, best classical volume configuration that we obtained using the greedy force approach. As you can see, the starting from number torsion 2, where we have the same result, we always are close to the best classical result. In the case of 6, we also beat the classical. This means that we are able to find the solution we find are in a good regime, so are good approximation to the classical best. But more interestingly, we can, as we can see on the right, the run times that compare the time it takes for the classical algorithm to bet the classical, the best classical volume, compared with the QPU, just the QPU time and the hybrid time, not the time to construct the Hugos, so just the QPU and hybrid time. And as you can see, the D-Wave and the hybrid solver in this case have a much, a great advantage with respect to the time of the best classical. And this is something that, as CINECA and Politecnico of Milan, we want to investigate more. This is a promising result since we compare the D-Wave and the hybrid solver with the non-parallelized version of the greedy approach and the brute force that could instead be parallelized. So that will be our next goal, to compare the hybrid and QPU with the fully parallel version of these other two classical. Thanks.